Today, probably the easiest day of this unit 0, we are going to graph and transform quadratic equations and other types of equations. So we're going to talk about like graphing. Where do the graphs come from? What creates the graph? Okay. Functions have inputs and outputs. This is going to show up any second now. When it does, I'll be excited. It didn't even, no, it's that frozen. There it is. Okay, graphing. Okay. The numbers, like x equals -2. You can look at the number x equals -2 on a one-dimensional number line. You see this number line? This number line can be used for x's. And x equals -2 would be plotted right there. Cool? The number y equals 4 can be plotted on a one-dimensional axis for y. You can say, hey, this is my y-axis, and even though it goes up and down, we can say 4. Cool? One-dimensional numbers get placed on number line. Cool. Functions don't have one dimension. They have 2 dimensions. We talked about how a function is like a machine. You take a number, you throw it into the machine. The machine does some work, and out comes a different number. For example, if I take the number -2, plug it into this machine, the machine will give me an output of 4. Now, what we get is a connection, a marriage for 2 numbers, an ordering of 2 numbers, a x value that also is connected to a y value. This, my friends, is 2-dimensional. 2 dimensions. It's got an x and a y, which is why we will not say, oh, x is -2, y is 4. We will combine our knowledge of the x-axis and this other y-axis to throw this point here in this 2-dimensional plane. 2-dimensional plane is an input plane. The input is typically the horizontal, and an output plane, the vertical. Now, what are some other like married sets of numbers that you get using this function f of x equals x squared? Tell me some other input, comma, specific outputs that go there. Tell your neighbors. Go. Got to be 2-dimensional. Very good. Very good. Plugging 1 into my machine gives me 1. So I have this 1 and 1. Plugging 2 in my machine gives me 4. So I have the married connection 2, comma 4. Plugging in 3 into my machine gives me 9. Plugging in 4 into my machine gives me 16. So I have a visualization of some of the like inputs and outputs on this 2-dimensional axis. We can obviously do -1, gives me 1, -2. We can do -3 squared is 9, -4 squared is 16. Now, we learn how to graph in like algebra 1, maybe even in middle school, but little do we kind of realize what we're doing and why we're doing. So what I actually am going to ask you to do is give me some more. Did anybody mention any other connected pairs of numbers besides -4, 16, -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, 9, 4, 16? Did anybody talk about any others? Well, figure it out. Give me some more with your team. Like, what are some other connected numbers? What are some other inputs that are connected to outputs besides those that we have there? Please do not go beyond our input axis of -4 to 4. So please do not go to 5 and 25. I don't want that. I want something else. No. I want between -4 and 4. Is it? I want some more. Give me some more. Who's got one? Kutchel, you got one? No? There you go. Beautiful. Thank you, Miss Ratty. We all are failing as American students. Italy is doing better at teaching their students than America is. Yo, 1/2 and a 4th. If I plug in 1/2 into my machine would output a 4th, whether it's -1/2 and a 4th or +1/2 and a 4th. Thank you very much. That's ready. Okay, keep going. Who can give me some more? A 4th and 1/16. Okay, we could do that. A 4th and 1/16. A 4th and 1/16. -1/4 and 1/16. We got symmetry. Cool. 2.5 and what? 6.25. 2.5, 6.25 is going to be right there. So obviously -2.5 and +6.25 be right there. Great, keep going. 1/3 and a 9th. Okay, so that's like right in between these two, right there. Okay, sure, we can do a 6 and a 36. That's another one right there. Okay, good. Okay, so that's right there, McCarty. Thank you. 1/1000 and 1/10,000. Okay, good. Here we go. Like, how about 3/2, 9/4, 2 1/4. So 1.5, 2 1/4. 1, 2 1/4, right there. That means -1.5, 2 1/4. What do you guys always do when asked to graph? You guys always stick to the whole numbers. And then your teachers say connect the line. Connect the dots, right? And then why? Why do you connect the dots? It's not because of a pattern. It's because there's infinite pairs that are there. They are the solution. If I kept asking you to give me more and more and more and more pairs, inputs and outputs, what would happen? You would start having more and more dots. And this is what I think math teachers should do more of, is yo, don't connect the dots. Add more dots. Why? Because these are connected pairs. They are an input plugged in, giving me an output. Boom. That's a dot there. That's a point. That's a input going to an output. What happens if I kept going? What would you have to do? Put more dots. What happens if you keep putting more and more dots down because you have more and more, you have infinite amounts of connected pairs? What then occurs with all the dots? Tell your neighbors. Yeah, it just kind of melds together. This is important. I think students, high school students especially, don't get that. I feel like sometimes we rush when we're teaching math. And especially when you use a graphing calculator. When you use a graphing calculator, it happens so quickly. You assume that it's like magic. If I graph f of x equals x squared, it happens so quickly that we don't realize what your computer program does is actually takes a lot of values and plugs it in for x, gets a lot of y's, plots those very, very quickly. It does not have programmed into it what x squared looks like. It does not just do the whole numbers. On your graphing calculators, it uses pixels, and we get that. Okay? So that's a little sidebar. Make sure we understand where graphs come from. Just like a collection, the infinite collection of all of our friends. Nice. Now, that y equals x squared or f of x equals x squared is the simplest form of the quadratic. The simplest, most basic form, we call it the parent function. This would be the parent function of a quadratic. It creates this U shape. And moving forward, we're not going to be like very specific. We're just going to be like, yo, it creates a U. So if like things are not perfect, don't worry. Don't even pay attention to like the y-axis anymore. It creates a U shape. If I went through the same process for y equals x or g of x equals x, I'd have the point 1, 1, 2, 2, 3, 3, 0, 0, negative 1, 1, negative 1, negative 1, negative 2, negative 2, negative 3, negative 3. Everybody starts with the whole numbers. You guys are smart enough to know, Thomas Ford, what happens in between the whole numbers? What do you have? A bunch more decimals that also can be plugged into the function that gives us points. Good thing Tommy's at the table. And if you kept going and kept going and kept going and kept going, all the points kind of meld together and creates that line. Okay, this is the parent linear function. This is a cubic function. That's funny. That's funny. He's doing hands up, don't shoot to the AP. 1, 1, 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. Okay, a little bit off. Yeah, what's it make? Yeah, good. Yo, we call that the John Travolta. Because he's staying alive. And then the negative is the negative John Travolta. You're exactly right. Negative 2 times negative 2 times negative 2, negative 3 times negative 3 times negative. It creates this kind of curve S shape. Cool. Now, we are going to stick to quadratics. Okay? So, quadratics and then maybe like random different types of functions that create funny graphs. And we are going to transform them. We are going to create new functions whose shape is still dominated by the parent function. And all we're going to do is just like math to our x squared. We're going to start with x squared, and we're going to do some math to it, which means we could add and subtract numbers inside or outside our square. We can multiply, we can divide by numbers, and that's kind of it. And what we're going to see is like what happens to the graph of my parent function if we add, subtract, or add, subtract in this way. So tell your neighbors, because this is review and you've done this before, what happens if you add numbers to x squared like this versus what happens when you add numbers inside x? You guys remember? You guys remember this? You remember this? Amen? Well, what do you guys think? Good, so it's good to understand. Okay, so I just heard a student say, man, like I knew this last year, but like I always memorize things and forget things. This is why in this class we try not to memorize, just understand. If I add 5 to x squared, what happens? Tell me right now. Let's see. Ready? X squared. Here you go, my x squared plus 5. You're right, it goes up. Okay? If I add 5 inside, what happens? Why? No, here's the question. Why does adding 5 here go up? Why don't I go left when I add 5 here? Why do I add 5 here goes left? Why am I going up or down? Start talking to your neighbors about that, and I want to hear some answers. Why does adding 5 outside go up? Why does adding 5 inside go left? All right. Okay. Ready? Why? Who's got an answer for me? Who's got an answer? Why? McCarty? Make sure you're being brave.
It's squared when it's inside the parentheses, and when it's outside parentheses, it's just not getting squared.
Why is it not getting squared? So there's something in mathematics that talks about how, like, the way in which we do things. And that's important. Oh, what is that? What is that, Lander? Order of operations, right? Order of operations says, yo, if you got an exponent, you got to do the exponent first. I'm going to take an x value, I'm going to square it first. We are starting with the graph of y equals x squared. We start with this graph, and then we add 5 to all the y's. Good. Y is adding 5 inside, and McCarty is exactly right. Like, you have to square like that plus 5, that x plus 5. But y is adding 5, pushing things to the left. You got to do parentheses first, sure, but why can't I just like say, yeah, adding 5 goes up, that makes sense, a positive y direction up. Why isn't this plus 5 pushing me to the right? What do you think, Brutton? Well, so it's got to be like x plus 5 being squared, right?
Yeah.
What do you think, Bussing? I like that idea. Bussing is like, yo, we got to kind of like zero things out. So that's an idea that I use. Anybody else over there? Any other ideas? I know McCarty does, but I'm looking over here. Do you guys have any other ideas? Higher? That's the right idea. And it comes back to Elander, who says order of operations. What happens first, the squaring or the parentheses? Parentheses occurs first, okay? So we have to do the x plus 5 first, and then we get the square, okay? Let's think about it. If this shifted to the right 5, then if I plugged in 5, I should get that 0 if this worked out. But the parentheses come first. Well, so I have to do the 5 plus the 5 first. Well, that's 10, and 10 squared is 100. So what ends up happening is, like, we gotta have to, do some ordering. We want a value that adds to 5 that zeroes things out, Bussinger, just like you said. -5 plus 5 has to occur first. And then we get to square the value. And this is kind of how I remember this. Is like, yo, what's going to negate the squaring? What's going to get rid of the squaring so squaring does nothing? Is if I plug in 0. If I plug in 0 into the parentheses, square 0. What's 0 squared, Toker? 0. Exactly. I know you're spacing out. Catching you. So what I think of when I'm doing this is like, yo, PEMDAS, thank you, Lander. Zeroing things out, thank you, Bussinger. Order of operations, what's inside or outside the square, thank you, McCarty. And I'm thinking, yo, that -5. That -5 is what's going to zero things out. That's why I know I'm shifting to the left side. Okay? So we are going to call things translations. Boom, I'm up. 5. That's G. Boom, I'm down 1. Don't think that it's wider or narrower. Like, it's not wider, it's the same width. I'm just going down one. We understand, because of order of operations, because we want to negate the squaring, that adding 1 to x actually shifts this left or translates this left. 1, again, like, we're not going to be very picky about things. It just creates the U shape, goes up. If I'm subtracting 2, well, positive 2 would negate the squaring. Give me a 0 squared. 0 squared is 0. Not something I memorize. I just kind of understand. Like, 0 times 0 is 0. If you plug in 0 and square it, you get 0. Positive 2 minus 2 gives me 0. That's why I'm shifting to the right 2. All right. If you understand order of operations, you'll understand what happens if you multiply values. Tell your neighbors, what happens if you multiply x squared by a half, 2, or negative 1? Which one's what? Gula, what if I multiply x squared by a half? What happens? So, what happened there? Did it stretch it out? Ooh, this is multiplying by a half. Here we go. X squared. We'll be able to compare the two. What happened? Now, you know what? You guys are missing. You're missing something. Order of operations. We were just talking about things first. What are we doing? We're taking an x. We're plugging it in, and we got to square it first because exponents come first. So I'm going to start with the graph of y equals x squared. And then I will take those values and multiply them by a half. Tell me, if you take the value of 16 and multiply it by a half, what happens to 16 when you multiply it by a half? Yeah, it becomes 8. What if you take 4 and multiply it by a half? 2. You are taking your x squared values, multiplying them by a half. That's making them smaller values. Don't memorize, guys. Think order of operations. We are not stretching things here. We are actually compressing things vertically. This is a vertical compression. We don't want to say we're getting narrower or wider because when we get to different types of functions in the future, namely in the second semester, we're looking at trigonometry. We don't want to talk about stretching. We're not going to talk about narrower or wider. Sorry, we do want to talk about stretching and compressing. That's a vertical compression. So now, what about multiplying your x squared values by 2? What happens? Tell your neighbors. Why does it stretch out? Why does it think order of operations? You have your x squared values. That has to come first because exponents come first. X squared values times 2. Your x squared values are like 2, 4, 3, 9, 4, 16. You're multiplying your x squared values by 2. What happens when you multiply numbers by 2? They get bigger. Woods, you got it? What happens when I multiply by 2? All my y values get bigger, and what I want you to do is go like this. Everybody look at me. I don't want this. I want this. My y values are getting bigger. I'm multiplying them by 2. My y values are getting smaller. I'm multiplying them by a half. Got it? X squared times 2. Yeah, they're going to be bigger. X squared times a half. Yeah, they're going to get smaller. Not this and this. Yes, it works, and you can memorize this, but like, let's think about mathematically what's happened. You're taking your x squared values, multiplying them by 2. Taking your x squared values, multiplying them by a half. Okay, so we're going to say this is a vertical stretch. What happens if you have a negative 1 times the x squared? You take your y values and you make them opposite y values. You take your x squared graph, multiply your values by -1, and they'll all become negative values. So you are right. We are talking about a vertical reflection. Now, pause. We are going to use the term vertical compression stretch, vertical reflection, but we're also going to use this term dilation. These are vertical dilation by a factor of whatever number. I'd call this a vertical dilation by a factor of a half. I'd say that vertically compresses things. I'd call this a vertical dilation by a factor of 2. I say that vertically stretches things. Okay? We showed the graphs, but like K is wider because you're taking your y values and multiplying them by a half. So we're compressing vertically. Here for V, it's yes, going to be narrower. I don't want to say that. I want to say my y values are getting multiplied by 2. So I'm vertically stretching. Okay? Cool. We're not going to worry about horizontal compressions and dilations yet because it's complicated, especially with y equals x squared. So that's it. Now all we have to do is be able to kind of like combine a couple at the same time. So tell your neighbors, what would the graph of this look like? Where would be the vertex of this if we understand transformation? Go. Thank you, Faye. Good. You are saying this is left 3, this is down 4. Why? -3 plus 3 will negate the square. It'll be 0 squared, then -4. So we are moving left 3, down 4. I'd probably want you to put -3, -4 there, and then just like a U. Got it? Everybody do G. Everybody do G. Wrong. On the left. F. Mike, don't be these guys. I will split you up if you can't handle this. We're doing G on the right. No. Nope. No, you can't. Order of operation. Parentheses, then the exponent, then the multiplication, then the subtraction. Yep. Yep. No. It's going to be a vertical compression. You're going to make your y value smaller, and you're going to reflect. All right, Grant Ford. Let me see. Where's your?
Before.
Cool. Don't do this, Mike. Don't do this. Let's not be perfect. Not be perfect. Write 4 up 1. Just say that's 4-1.
All right.
Okay? Don't put tick marks down. It's not worth your time. Okay? No tick marks needed. Rock. No tick marks needed. Just be like, yo, that's like 4-1. And I'm going up. Got it? Order of operations. I'm taking my x values and squaring them. Boom. So I start with y equals x squared. I'm multiplying that by 2. So boom. Vertically stretching. I'm making my y values larger. And then I'll subtract 3. Happens to be like you can work at these at any order that you want. But I'm thinking vertically stretching and then shifting down 3. So something like that. Order of operations. X is being squared times 2 minus 3. I'm taking my x squared graph, stretching it, and then subtracting 3. I'm not going to go right or left at all. Start with your x squared graph. Now, this is different. We got to start inside things. We got to think about, yo, what is the x value that can negate the 0, that can zero things out? We start with that. Then we're going to be multiplying all of those x squared values by -1/3. What happens there? And then we will be subtracting 2. What happens there? Tell your neighbors, where's our vertex? What's it look like? Explain it. Oh, careful. Double R. Careful. Run. Beautiful. Just label your vertex, okay? One extra thing, you got to pay attention, inside, outside. What's going to negate the squaring? Like, what do you plug in for x so that it zeroes things out? -3. -3 is the x value. That's how much you're shifting left. You got it, man. Okay. Yo, x equals negative. Oh my goodness. What? Are you kidding me? Let me see your work. Give you your phone. Yes, I told you backpack devices over there. You're on a temporary phone suspension during the rest of the class. Outside. X equals -3 negates the 0. Left 3. Down 2. Okay, we can worry about the down 2. Multiplying your x squared values by -1/3 flips them and makes them wider. I'm down 2. I should be at -3, -2. I saw too many people mess this up. And I'm not going to give you the rule. I'm not giving you the rule. I'm not saying inside x is opposite. Outside y is normal, you know? But that's the rule. I know. All right, here we go. So, what we learned is that, and you're on the next page, if you take a function and add a value to it, you're going to be going up or down. If you take a function and change the insides, that's going to be changing the left and the right. If you take a function and multiply it by a number, you're going to be vertically stretching or compressing because you're taking your function values and multiplying it by numbers, okay? Now, on the next page, we are going to take an equation like f. We are going to shift it up 3 to create the equation D. Well, to shift things up 3, we will add 3 to the outside. It'll take the y values and add 3. If I want to, I could say, well, f of x is just x squared. X squared plus 3 is x squared plus 3. I've just created the function D. Let's do the same thing to the graph or the equation for g. If I want to take g and shift it up 3, give me the new equations for E that's created. You got it? You got it? Check with your neighbors. That's the key. We are collaborating. Everybody collaborate. What is the equation for E? I'm taking the graph of G. I'm shifting it up 3. What do you think you're going to get? Ready? I want to take G, their values, add 3 to them everywhere so that I get the values 3 more. Like the y's are going to be up by 3, which means I'm going to take the equation x squared plus 2x plus 3 and add 3 to it. I just get x squared plus 2x plus 6. Add 3 to G. That's it. Cool? Here comes the next one. I want to shift things to the left 3. Well, I understand that if I, in my function, want to shift things to the left, well, I'm going to have to start by plugging in -3, so that -3 plus 3 zeros out my function. So I know f of x plus 3 will shift things to the left 3. Well, that means this L equation will be using x plus 3 and squaring it. Could you do the same thing for G? Could you do G of x plus 3? What would that look like? Write down what you think it would look like if you got it.
You can't make me.
Who's got it? Who's got it? Good effort. So it's like close. Very close. True pick.
Is it 1 after that?
Nope. I'm just shifting things to the left 3. Who else has an effort?
I don't know.
No. We have the x squared plus 2x plus 3 equation. I want to shift this to the left 3. We can't add 3 to the outside because that's taking my y values and adding 3. This is shifting it up 3. I want to negate things so that when I plug in -3, it's like plugging in 0. How can I do that? Ready? Ready? X plus 3 being squared, very similar to this. Plus, to negate, like think about plugging in 0 into this, you'll get 3. If I plug in -3 into this, I need to get 3. I will have to also add 3 inside of that x too. 2 sets of parentheses. Most people don't pick this up until you've done it a couple times. Yep, and your homework. And your test. Okay, what if we want to vertically dilate F and G up top by 2? What do you think you're going to get? What if I want to vertically dilate this by 2 and I want to vertically dilate this by 2? Tell your neighbors what do you think you'd get. Don't just sit there and like wait for this class to be over. That's almost perfect. It's just vertically stretched. It's just multiply your y value. Let's see, Nancy. Nailed it. I would just say +2. We don't have to flip the sign. But you actually are vertically dilating and shifting left. So you get the right idea. You're making it too complicated.
right? Is that how you do it?
No, you're doing too much. Like we're going all the way back up to this equation, x squared. Not the previous one. We're going back up to the top. That's confusing. I'm glad we're clearing this up for the next class. You nailed it. Thomas has got it. You're close. That's going to shift it up, adding to my y. Vertically dilates means vertically stretching. Has everybody tried? Have you tried? Let me see the bro table. What'd you guys put down?
No.
You are so close.
So,
What do you think it is? No, you have the same thing. Ready? Nope. Ready? Here we go. If you want to vertically dilate, you're just multiplying your y value. Okay? So I'm like multiplying my y value by 2. So here, I'm multiplying my y values by 2. That's the f multiplied by 2. If I want to vertically stretch my y values by a factor of 2, I need to multiply my function values by 2. I need to multiply my function values by 2. 2x squared plus 4x plus 6. Yeah, because you forgot the 6.
No, you agreed with me when I set up my reason. You were like, yeah, maybe.
Great question. Trupik asks, would you accept this? Yes, I would. But maybe on a multiple choice question, Trupik, you see that. All right. We take f. We vertically reflect it. Then we shift it down 5. We take f. We vertically reflect it. Then we shift it down 5. That makes sense? We take g. We vertically reflect it. Then we shift it down 5. You need to take g. Vertically reflect it. Then shift it down 5. What you will find is that if you just keep with notation, this is easier to do than if you're just trying to figure it out yourself. Now, that would be negative x squared minus 2x minus 3 minus 5, which would be minus 8. Watch what happens if I did it in opposite order. Take g, shift it down 5 first, then vertically reflect that. You would end up with a different answer. Okay? You will see these on your homework. It's just like we'll use notation to help us. The last is something that shouldn't be too crazy. Just like, if I give you a random graph, would you be able to know what is being done and what would happen to the graph? So tell your neighbors, if you take this graph m, you take m minus 2, what does that look like? What happens? What happens? If you take your graph of m and you subtract 2, what happens? Everything moves down 2. Bingo, bango, bongo. Now, I do want you to keep track of things so that it looks nice. This would be negative 2. Here's your m. If you take your graph, your m values, and you multiply them by negative 1, what graph does it create? Draw it. Draw it. Draw it. Draw it. Draw the next one. Draw this one on the bottom left. What happens? What do you get? Wait. Where's the W? Down here, all of the Y values get flip. I think once we get to stuff that's a little bit more complicated, you guys might struggle a little bit. We're going to shift m over 1, and we're going to multiply by 2, making this up to 4. Taking this value and going up to 6. The easy stuff is easy. You guys struggled on the more complicated stuff. I don't know. Some of you. Struggle.
I don't know if I'm going to do it for sure. I'm going to talk to my parents, but
Okay.
it would be nice.